Hello, and welcome to our discussion of curves. A curve, or a path, or a contour in the complex plane is a map or a function, gamma, from a closed bounded interval a to b in the reals into the complex plane that is both continuous and piecewise continuously differentiable. In other words, gamma is in C1 piecewise of the interval a to b and also continuous on the interval a to b. The initial point of gamma is the point gamma of A. The terminal point of gamma is the point gamma of B. The image of gamma is the set of complex numbers gamma of t for t between A and B. A curve is closed if gamma of A equals gamma of B. And if we have a subset capital gamma of the complex plane, and if there is a curve little gamma from an interval a to b in the reals into the complex plane such that big gamma is the image of little gamma, in other words, big gamma is the set of all points of the form little gamma of t for t between A and B, then we call little gamma a parametrization of big gamma. Last, a curve is simple if it is one-to-one or injective on the interval closed at A to open at B. In other words, if T1 and T2 are distinct points between A and B, then gamma of T1 is not equal to gamma of T2. Here are some pictures. Here is a continuously differentiable curve. You see that the image is smooth. There are no corners in this curve. Here's a continuous curve that's piecewise continuously differentiable, but that's not continuously differentiable because we have some corners here. Here is a simple closed curve. You note that the starting point is the same as the terminal point, no matter what you pick the initial or terminal point to be. And you also see the curve does not intersect itself. Here's a closed curve that is not simple because sort of in this sideways figure 8, you see the curve does double back on itself. Here's one fundamental example. Fix a point z0 in the complex plane and a real number r that's positive. Let's parameterize the circle, which is the set of all points z such that the modulus of z minus z0 equals r. So first, fix such a point z, so the modulus of z minus z0 equals r. That means we can write z minus c0 is equal to the modulus of z minus c0 times e to the I times the principal argument of z minus c0. So we've just written the difference z minus c0 in polar coordinates. Now the modulus of z minus c0 is equal to r, so we get z minus c0 equals r e to the I times the principal argument of z minus c0. And we solve for z. Z equals z0 plus r times e to the I principal argument of z minus z0. And let's put t equal to the principal argument of z minus z0. So then we have minus pi is strictly less than t is less than or equal to pi. And more compactly, we've written z equals z0 plus r times e to the it. So this suggests that the parameterization of our curve should be gamma of t equals z0 plus r times e to the it. Now, one thing we need to be careful about, the domain of a curve should always be a closed bounded interval. This is the definition and convention that we choose to work with for curves. It'll make a lot of things in life easier later on. We've only taken t in this half-open interval, open at minus pi and closed at pi. But what do we know from just trigonometry? z0 plus r times e to the I times minus pi is of course equal to z0 plus r times e to the I pi. So we might as well just take the domain of gamma to be the whole closed bounded interval minus pi to pi, and the curve will intersect itself when t equals minus pi or pi, but that's fine. And so what have we done? We've shown that for all points z in the complex plane with the modulus of z minus z0 equal to r, there is a real number t in the interval minus pi to pi, such that z is equal to gamma of t, with gamma defined above. Conversely, if you have a number z equal to gamma of t, then you can calculate directly from the formula for gamma that the modulus of z minus c0 equals r. And so all points of the form modulus z minus c0 equals r are equal to gamma of t for some t between minus pi and pi. Gamma parameterizes this circle. This is a parameterization well worth knowing and memorizing. For another example, take points z1 and z2 in the complex plane. Then the line segment from z1 to z2 is going to be the following curve. Gamma of t equals 1 minus t times z1 plus t times z2 for t between 0 and 1. And we will often refer to this curve with the notation closed bracket z1, z2, closed bracket. Now, of course, that looks like the notation for an interval on the real line, but the idea is that this closed bracket z1, z2, closed bracket really represents a function defined on the interval 0 to 1. So what's the difference between the functions gamma 1 of t equals 1 minus t z1 plus t z2 and gamma 2 of t equals 1 minus t z2 plus t z1? And they're both defined on the interval 0 to 1. So both look like parameterizations of line segments, but the way the z1 and the z2 appear is different. Now, it's probably the case that gamma 1 and gamma 2 aren't the same. I mean, we just calculate gamma 1 of 0 is z1, and gamma 2 of 0 is z2. So unless z1 and z2 are equal, gamma 1 and gamma 2 are not going to be the same function because they have different values at the point t equals 0. But it turns out they have the same image. Namely, the set of all points of the form gamma 1 of t for t between 0 and 1 is equal to, by definition of gamma 1, the set of all points of the form 1 minus t z1 plus t z2. And I claim that this set is also equal to the set of all points of the form 1 minus tau z2 plus tau z1 for tau between 0 and 1. And this third set is really the set of all points of the form gamma 2 of tau for tau between 0 and 1. So what do we see here? We have two functions or two curves that have the same image in the complex plane. The set of outputs is the same, but the functions are not the same. Namely, if we go from z0 to z1 with gamma 1, we're sort of starting at z0 and going up all the way to z1. Whereas with gamma 2, we're starting at z1 and going all the way down to z0. So what do we see here? There is a notion of orientation that is different between gamma 1 and gamma 2. Gamma 1 and gamma 2 cover the same span of points, but they do so in a different order or orientation. One of them starts at z0, the other starts at z1. So curves fundamentally have a notion of orientation. They start at an initial point gamma of A, they end at a terminal point gamma of B. And so a curve is a directed set, unlike the image of the curve, which is just the set of points living out there in the complex plane.